Okay, so we're going to look at this idea of Snell's law over here, which gives us that basically what happens when you're going from one medium. Now, in each case, we're talking about an optically, we talk about optical density, not necessarily relating to the word density, but it's the amount of material will actually slow down a wave. So, if you've got, for instance, light going through, when you've got a high, these N over here are called our refractive index. When the refractive index is high, it means we say we've got a high optical density. It slows it down. For a vacuum and also air, we say that our N is equal to 1. Our refractive index is equal to 1. And the velocity of light, in air, we give the symbol c, and that's about 3 times 10 to the 8 meters per second to -1, or about 300,000 kilometers per second. Now, when light goes into another substance, so say you've got light, and I'm just going to draw it directly in here. It's coming in, it's going from air to glass. What happens is that it slows down. Now, when it's going in at 90 degrees, when this is 90 degrees, it will just continue to go, and we won't see any deviation at all with that light. But the velocity will change. So here it may be 3 times 10 to the 8 meters per second. Here it may be 2 times 10 to the 8 meters per second. It's slowed down. All right? Now, the refractive index of the one to the other is given by this formula. Yeah.
So the refractive index is always given in terms of fraction of speed of light in a vacuum.
Yes, yes. So, for instance, here, if this is my N1 and this is my N2, now you have to label these. You have to choose the label. So I've chosen the air to be N1, and therefore this will be V1, obviously. All right. This is N2. This will be V2. Okay, so now we have our formula over here. I'll do it over here. Our N1 over N2 is equal to V2 over V1. Now, if I want to work out my refractive index of in glass, my N2, obviously my N2 over N1 was equal to the V1 over V2. I just invert both sides. And I continue down over here because my N1 is equal to 1. That's equal to 1. Taking it is equal to 1. So I'm going to have N2 is equal to 3 times 10 to the 8 divided by 2 times 10 to the 8. I'll have a refractive index of 1.5. Now, what will be the unit for that? What's my unit for refractive index? No unit, because you're dividing speed divided by speed. All your units are going to cancel, so it doesn't have a unit. It's a ratio. All right, and it's a ratio to do with the velocity. Yeah.
Can I just ask, how come it's in vacuum and in air it still equals to 1?
There is a slight change, but for our purposes, we take it to be the same. Yeah, yeah. It gives an indication of a slowing down as it goes into a medium. Yeah.
So why is it that the light slows down in different materials? Like, what is behind the slowing down?
If you look at the speed of light, it's based on two different values. It's the permittivity and permeability, which are basically to do with the electric and the magnetic fields. And in different materials, those values, those constants, take on different values. And so the permeability, the ability for the electric and the magnetic field to be formed in those substances change as you go, and that affects the speed of light. I can show you the formula and explain the formula to you further. Okay, so now one thing I want to look at is this idea here, is that the velocity is equal to frequency times wavelength. So as your velocity, here you got your velocity change. It went from 3 times 10 to the 8 to 2 times 10 to the 8. What about, because it's equal to frequency times wavelength, velocity is equal to frequency times wavelength, what happens to the frequency, what happens to the wavelength? And doing this, I want to just discuss this idea of frequency in a little bit of detail. Okay, so I want you to imagine here, imagine that we have got some sort of conveyor belt. I just want to bring up a new page here. So I just want to bring up a common page so I can work on. Here we are. Okay, so I want you to imagine the situation. Say if you've got a conveyor belt, you know what a conveyor belt is. So you've got a conveyor belt like that, it's turning, and it's going in this direction with a certain V1. Alright? And you've got another conveyor belt over here. A conveyor belt. It's a, you know, like those things in the airports that you stand on, and it takes you along. That's like a conveyor belt. All right. So sometimes they use these things in factories. I don't know if you've been in these factories, and they're transporting all the stuff. It's an easy way to transport all the stuff. You know, your sweets and your chocolates and so forth. You see them all going along like that. Okay. And this one over here is going at V2. Now, let's say V2 is greater than V1. All right, so this conveyor belt is moving faster than that conveyor belt over there. And say we've got some sort of device over here that's dropping the articles in at a constant frequency or a constant period. So we dropping articles on here, and because they're coming on at a constant period, they are equally spaced. So these are equally spaced here. That spacing there. I'm going to call that lambda 1 because we're going to relate it to wavelength. Now, as it drops on this conveyor belt, this one's going faster. What's going to happen to the spacing? All right, we would imagine that the spacing here is going to be larger, will it not? Because this is going faster, so it drops down and it moves further. Yeah. No, but this is a constant velocity. So it's coming off an equally spaced. So these should also be equally spaced, and this we'll call lambda 2. And then we've got a box over here where they drop into. These things drop into here. One's busy dropping off at the moment. Okay, so we got them dropping in. Now the question I want to ask you is, at what frequency, the number per second or per unit time, are they dropping in here? If I call this frequency 2 and I call this dropping out here frequency 1, they're dropping out a certain frequency, a certain number per time. They're dropping in here a certain number per time. This has been going for quite a while. What can you say about F1 and F2? They must be the same. Why must they be the same? All right, the distance is bigger, but it's going faster. All right. I mean, you can't have it different because otherwise you've either lost some of these things in the process or you've added some things in the process. You've got somebody stealing sweets, I suppose they could, along the way. Then you'll see that the frequency would be changing, so you have a problem there. So the thing is that the frequency, those two are the same. The frequency stays the same. So the frequency is constant. And that's what happens when light goes from one medium to the other, the frequency remains constant, but the wavelength changes. And because your velocity is equal to frequency times wavelength, like that, you can see that the velocity and the wavelength are directly proportional. So as you increase the one, you decrease the other. So if I've got V1 and lambda 1 and V2 and frequency and lambda 2, then I can say that the frequency of both of them will both equal, the frequency of this will equal V1 over lambda 1, and that will equal, frequency will equal V2 over lambda 2. Okay, so when I get my formula, my Snell's law formula, remember we had N1 over N2 is equal to V2 over V1, all right, like that. I could also say that's equal to lambda 2 over lambda 1. The wavelength. It would follow the same, you see. It would stay the same because that's because, let me just add one more step here. Because velocity is equal to frequency times the wavelength, and this one's equal to frequency, sorry, 2, that's a 2, and like that, then you can cancel out that and you get your lambda 2 over your lambda 1, like that. Okay. Okay.